Okay, so today let's try to solve another LeetCode problem, maximum product subarray. So given an integer array numbers, find the contiguous subarray within an array which has the largest product. And it's guaranteed that the input array contains at least one number. So we are given two examples here. In the first example, the input array has values 2, 3, minus 2, and 4. And the output is 6, which means within this input array, we can find a subarray which has the largest product, 6. So how this 6 is calculated? Let's take a look. So the input array has numbers 2, 3, minus 2, and 4. So if the subarray only has one element, the subarray could be 2, 3, minus 2, and 4. And the subarray that has the maximum product will be this one, and the maximum product will be 4, right? Now we increase the size of the subarray to 2, and since all the elements in the subarray needs to be contiguous in the input array, so the subarray could be 2, 3, 3 minus 2, minus 2, and 4. So we can see the product of the second and third subarray will be a negative, comparing to our current largest product. It will be less than the current largest product. But the first subarray will generate a larger product, which is 6. So we need to update the largest product from 4 to 6, right? What if the subarray has 3 elements? Then the subarray gonna be 2, 3, minus 2, and 3, minus 2, and 4. As we can see, the product of these two subarrays will be a negative, comparing to 6. These two subarrays won't contribute the largest product. So now let's move to what if we have a subarray that has 4 elements. So in this case, the array itself becomes the subarray, which is 2, 3, minus 2, and 4. The product will become a negative, right? So 6 becomes our final largest product, and the subarray will be 2 and 3. So now how can we find an algorithm to help us find the largest product? So as we go through the examples here, one idea comes to my mind is we just need to list all the possible subarrays. And then we calculate the product for each subarray and keep updating our largest product, right? So in order to do that, we need 2 pointers. The first pointer, let's say, is I. So when we start from I, our subarray could be 2, 2, 3, 2, 3, minus 2, and 4. And after that, we move our pointer to I plus 1, right? And then our subarray becomes 3, 3 minus 2, 3 minus 2, and 4. So we can use a second pointer j here to help us to get the subarrays. So eventually this will become an O(n) squared time complexity solution. And since we won't create any data structure to help us get the output, so in terms of time complexity, it's 01, right? So let's code it. So this won't be an optimal solution, obviously. It will get the limit time exited error, but let's just give it a try. So we need to define a result, which is our current largest product. Initially, let's set it to the minimum value of 32 bits integer. Oops. Okay, so we need a second pointer which starts from I. And we need a temporary variable here to help us keep tracking of the product. Let's say is temp. We set it to 1 because 1 won't impact the product. So temp 1 will times our current value. And every time when we have a new product, right, we need to updating our result. Eventually, we need to return the result. Okay, so if we submit it, we will have the time limited exit error. So how can we improve the algorithm? So I think we can use the DP, dynamic programming technique, to solve the problem. So the idea of dynamic programming is we divide the big problem into smaller and easier sub-problems. And then we try to find the optimal solution for the sub-problems. And eventually we use this optimal solution for the sub-problems to come up with the optimal solution for the entire big problem. So that's our idea. Now what's going to be our sub-problems, right? I think we can define such a sub-problem, which is at index, say, I, right? Can we find a subarray, and that subarray has the largest product, and what the largest product is, right? If we find that result at index I, and when we calculate the next largest product, we can reuse the result we calculated at index I for index I plus 1. Right? In order to do that, I think we need to keep tracking of the maximum product and mean product, that including the value element at index I. So when we go to index I plus 1, if numbers at I plus 1 is a positive number, right? Then our next largest product could be this number times that maximum number. But if that number is negative, right, it could be that number is negative. So in order to get the largest product for the next position, we need to time that number with a mean value. Right? The mean product that including the value at index I. Oh, this should be I plus 1. This should be I plus 1. Right. And lastly, the number at I plus 1 itself may become the max, the subarray that can generate the largest product. So the number at index I plus 1 itself becomes the subarray that will generate the largest product. Like for example, we have array like 0, 0, 4. So before we visiting the last element 4, the largest product will be 0, right? So in this case, when checking the last element 4, this last element itself will form a subarray has the largest product, which is 4. So this is the DP solution, and these three relations here becomes our state transition equations, right? And let's code it. Okay, so we need to define two DP array to track the maximal and the minimal product that including the number at a certain index. Right? We also need to have a variable to keep updating the largest product. Let's say it's result. Okay, result, same as before, is the minimal value of the 32 bits integer. Now what's going to be the base? Max 0 is our first number in the array. And same for the mean DP array. Okay, then we just need to fill in the max and mean DP array, and meanwhile keep updating our result. Okay, as I mentioned before, there are three possible options we can have to get the new largest product. The first one is the number itself becomes the subarray that has the largest product, right? The second case is we need to use this current number. Oops. To times the maximal product that include number at I minus 1. And the third case is we need to use the current number to times the mean product that include the value at index I minus 1. Right, then we just need to keep updating our DP array, max and the mean. So we need to find the max value between P1, P2, and P3. Similarly, we need to update the mean DP array. Eventually, we need to keep updating our result. Okay, after we checking all the possible, after we checking the last element, we will get our answer. So we return it. Line 19. $17, okay. Oh, max at I. Max at I. Okay. Yep, so let's submit it. So the answer is wrong if the input is -2. Why I'm returning this? Oh, so let me give the result as 0, number at 0. Yeah, because we need to find the subarray, right, of the input array. Yeah, sorry. This should work. Okay, so it works. And comparing to the previous brute force solution, we just need one pass, right? So it will be a time complexity O(n) solution. But we're gonna introduce two DP array to keep updating our max and the minimal product. So time complexity will be O(n). Do we really need to maintain two integer array here? No, we don't, right? So what we care about is what is our maximum product and minimal product. We just need two local variable. Right, so instead of using the index, we just keep tracking of the current maximum and the minimal product. Okay, so this solution, let's first compile and submit it. Okay, so you can see after the change here, time complexity will be the same as before. But the space complexity will be O1 will be a constant since we only introduced 3 variables here instead of using 2 DP arrays, right? So yeah, this is a good problem, and I really enjoyed it.